Hello guys, welcome back to Learning Solidity. So in this video we'll be talking about sending Ether to a smart contract. So I'm creating a Solidity project here, and I'll just increase this a little. And my version of Solidity, primary Solidity, let's use 0.68, I guess. Let me just add this here. There are three ways to send Ether from a smart contract to another smart contract or address. The first way is the transfer, and the second is the send, and the third, why do you keep doing this? The second is the send, and the third is the call method. So what are the difference between these three? Why are there three ways of doing this? So the transfer method and the transfer and the send method have a fixed amount of gas. So the transfer method has a fixed amount of 2,300 gas. That's the maximum gas this transfer method uses, and it throws an error if there's an error in the smart contract. Like if the transaction was not successful when transferring Ether to a smart contract, if for some reasons the transaction was not successful, the transfer method throws an error, reverts the state of the contract sending the Ether and the contract that is accepting the Ether. So this becomes, it throws an error. Let's just do this way. On send, on the other hand, also have a maximum of 2,300 gas it can use, but the difference between this is that the send method returns a boolean, either true or false, depending if the transaction was successful or not. So it returns boolean, or I should just leave this as boolean. Boom. The call method, on the other hand, lets you to be able to specify the amount of gas you're willing to use. And the call method, if you've watched my call method video, you should know that the call method returns two values. The call method specify amount of gas, and it returns a boolean. It returns a tuple, a boolean, and bytes. Byte is the return value from the function we called. The transfer and send method protects your contract from re-entrancy attacks due to the low fixed gas. We'll talk about re-entrancy attack down this video. Just hold on. So the whole reason for the transfer and send method were introduced was to address the cause of the infamous hack of the DAO. I don't know if you know about that hack, where 3.6 million Ether were stolen from a smart contract using the re-entrancy attack. So the idea is that since the transfer and send method have just 2,300 gas to use, which is exactly what's needed for transferring Ether, if a user try using the re-entrancy attack, there will be no more gas left for the user to use to attack your contract. Problems start arising where developers start building complex projects. In their fallback method, you might want to change the state of a variable, and because the gas specified is only used for sending transaction, you're not able to change the state of a variable, and then the transaction will keep failing. Which brings us to the call method. But before we talk about the call method, let's create two contracts, a sender and a receiver, so we can understand these two methods. So I'll create a contract, the first contract. This should be the sender contract. This contract will be the one sending the Ether. So in this contract, we need three blocks. The first is the constructor. I'll just create a constructor here, variable, and it does nothing. I just want to be able to send Ether to this contract when deploying. Since this contract will be the one distributing Ethers, you need to have Ether to it. So I'll make this public so I can call it. I'll create a function balance, which should tell us the balance of this contract. So function balance and public, and it returns a uinst. Basically what it just returns is address of this balance, and we can make this view, can make this a view, and the third function will be the fallback function. So we use the receive, and is external, and it's also payable. So this fallback function is just to receive the Ether. So the sender contract is complete. We need to create a receiver contract. So the receiver contract, sorry, my bad, this should be in the receiver contract because this is the one receiving the contract. Sorry. Okay, so the receiver contracts have a fallback function, and it should have a balance function. I should just copy this to check the balance of the contracts. In the sender function, we need to send ETA to this contract, to this receiver contract. So we need functions for that. Since we are talking about this too, we need two functions. And the first will be, let's see, the function will be send with transfer. And it just takes the address, the payable address of the contract we're trying to send ETA to. So let's call this address. And we'll make this public. And it shouldn't return a value. All we have to do is call the address, and we transfer, let's say 0.001 ETA. ETA is a keyword in Solidity programming language, so we're sending this amount of ETA to this contract. And I'll copy this, we'll do it for the send method. And instead of transfer, we use send. And here also we use send. Remember, the send function returns a boolean, so right here we can return a boolean, so we can know if the transaction was successful or not. And right here we can create a boolean for the send, and down here we return the send variable. Okay, so this is it for the two functions. Okay, so we're deploying this contract. I'm deploying the receiver contract. Deployed. Now I'll deploy the sender contract. Since I made this payable, so we can initialize some ETA to this contract. So I'll specify, let's give this for ETA. Okay. Alright. So if you check the balance of this, we can see for ETA, Solidity converts it to wave, since wave is the default unit. So it converts the ETA to wave, so this is what we get. So this is for ETA. If we check the balance of the receiver, we should get 0. Nothing is there. So let's try sending ETA to this contract. We need the address. We've copied the address right here and paste this. Once we send this, we can see the transaction is true because we returned the value, which is true here. And if we check the balance, we can see we have some ETA here. And we should do the same thing with the transfer method. Also successful. If we check, it should double. Yeah, it doubled, so it works. We have no problem using the transfer method because it uses 2,300 gas, and what we just did was to receive ETA. We did not change any state variable, so the gas was enough. But what if we have a state variable in the receiver? Let's see, and let's make this public. Or let's just say 2 state variable. So in the fallback function, we can change the state variable. Let's give this 9, and the B, let's give this 10. Okay, so since it's only the receiver we changed, the sender is still okay. We can delete the receiver and redeploy the receiver. Okay, we just need to replace the contract address. If we check, this should be all 0. My browser was having issues, so I had to switch browsers. So we've added a state variable, we've added state variables, and we are trying to change the state of these variables. We'll deploy these contracts. Let's deploy the receiver, and as for the sender, let's give it 3 ETAs, and we'll deploy this also. Okay, so if we check, the variables all should be 0, yeah, and this should be 9, and this should be 3 ETAs, and we should send ETA to this contract. We copy the address, and once we paste it in here, we should send ETA here. Let's just drag this up a bit. From the look of things here, the transaction was successful, but if we should check the state variables, nothing changed. They're still zeros. If we check the balance, it's also 0. We have to check that transaction. Once you look at the transaction, you see the return, the output is false. So this transaction was not successful because the gas was not enough to change the state variable. If you check with the transfer also, the transfer should return an error because as you see here, the transfer throws an error. It doesn't return a value, it throws an error. So it refers the state of the variable, it throws an error. This should still remain zeros, and this should still remain what it is. So now this brings us to the call method. The call method lets you set the gas for a transaction. We'll create one more function. I'll copy this. So we'll call this call with the call method and returns boolean call, and we are specifying the value as this. We can also specify the gas, and in here we can specify the gas, but the thing is that you might not know what the contract you're signing to. You don't know what it's doing. You don't know the amount of gas it needs. You don't know how much it costs for single change. You don't know how much it costs for double change. So you can't specify a specific gas for this. So which means you have to use all gas. So I'll just close this. We are using all gas for the transaction, and we have to do this because we're calling the fallback function. So this returns two values. It returns boolean and bytes. So we have to do the cent and the bytes. We'll call this results, and it's a tuple, so we have to put this like this. And I don't think this is needed. So we can return the send variable. Since we did not change the receiver contract, we'll deploy just the sender contract. And we can delete the sender contract from here, and we'll deploy the sender contract. Let's give it, since we're not using much, let's just give it 1 eta and deploy. If you can see, the balance is 1 eta, and if you start calling with this method, transfer throws an error, send returns false, send returns false, and the call method works. As you can see, it returns true, it works. So if you check the balance, it should reduce. Yeah, it will reduce. And if you check the balance here, it should increase. And if you check the variables here, they should have some values, as you can see. So the call method is the recommended function to use when transferring ether, because it forwards all the gas and minimizing any chance of error, as a transaction might need more than 2,300 gas to function, to run completely. But there's a pitfall with the call function. It leaves you open or vulnerable to reentrancy attacks. When using the call function, you have to write a guard that will prevent reentrancy attack. So what is reentrancy attack? We've been talking about it since the beginning of this video. A reentrancy attack is when the function, in our case, this function, calls an external contract function, which is this fallback function. This fallback function will recursively call this function. So this will be a recursive loop. These two calling each other. The only way it can stop is if the gas has been exhausted, or if this contract runs out of ether. There are two ways of reentrancy attack. The first way is a single function attack, and the second is a cross function attack. So a single function attack is the simplest and easiest to prevent. It happens just what we explained right now, when these two keep calling themselves. Like this is a vulnerable function, and it calls this contract. This contract now recalls the vulnerable function, so it becomes a loop. Why a cross function attack? Maybe you guessed it, is when this function calls this function, and instead of this function to recursively call this function, it calls another vulnerable function in the smart contract. Maybe a change ownership function, or maybe just another variable function in smart contract. Maybe a transfer function or something else in the smart contract. That's a cross function reentrancy attack. Since this video isn't a dedicated video on reentrancy, we'll just talk about the single function attack, and maybe some other time in the future I'll make a specific video, a dedicated video for reentrancy. So we'll modify the receiver function. For that, we'll create a variable. This variable will hold the vulnerable contract, which will give us VC. And since we don't know the contract until we deploy this contract, we'll create a function that will update this contract for us. So let's call the function here. Let's call this function set VC, and this function takes an address, contracts, and it's public, and it doesn't return a value. So it just updates VC. VC should be whatever contract user passed. Contract here. So this is it. We'll still leave the balance here. We'll still leave the fallback function here. And another thing we need to do is to create an attack function. So this function will be the one to attack this contract. So let's create a function. We'll call this function attack. It should be internal. There's no need making it public since we are not calling it from outside the contract. It should be internal. And right here, since we have the address of the vulnerable contract, we can still use the call method to call back this contract. So to do that, we just have to use the vc.call. And since it's not a payable function, we don't need to pass any value to it. What we have to do here is abi.encode with signature. The first parameter is the header of the function we're trying to call, which is this. So we just copy this. And this takes an address. So we have to pass in the address here, address. And the second parameter is the value of the address. The address has to be this receiver contract address. So we can convert this keyword to an address. You just have to call the attack function. Okay, what's the error right now? This should be an address data type. Deploy the contract, receiver contract, and the sender contract. Give this one ether and deploy the sender contract. If everything is correct, we should be able to hack this contract and strip it off everything it has. So in the receiver contract, we need to initialize VC. So we'll copy the sender address and initialize VC. Transaction was successful. If you check VC, it holds the address of this contract. So once we call with, we need to copy the receiver address and try sending ether to the receiver address. So once we send the ether with the call method, because it has enough gas, if you check down, it's pending, it's doing a recursive loop till the gas is exhausted. So it's completed right now. If you check the balance of this contract, so this was the amount it could take before the gas was exhausted. And if we check the balance here, we have 0.9. So it kept doing recursive call till the gas was exhausted. But what happens if you try using the send method? Because of the low gas, it could not do a recursive call. So as it could not do a recursive call, it could not hack this contract and steal off the ether from the smart contract. So when using the call method, make sure you have a check against reentrancy method. How do you prevent reentrancy attacks? So a way to go about this, a way to prevent this reentrancy attack for this particular contract is to find a way to know when the user has already called this function. So to do that, we'll create a public variable here. We'll call this boolean and we'll call this locked. Let's call this locked, and it should be set to false. And right here, the very moment the user calls this function, we'll set it to true. Once we set this to true, down here we can set it back to false. Then down right here, we require that the contract is not locked. So I'll deploy the two contracts back. The receiver, the sender, give it one ether, deploy. Okay. Copy the sender address, initialize the VC, and check the balance 0. VC show the address, check the balance 1 ether, and once we try calling, let's copy the address of the receiver. Once we try calling this, we get an error. This is because the reentrancy was detected. What happened here was, at the start, locked is false, which means the contract is not locked. So when you try sending this, it checks if the contract is locked. Once it checks this, the contract is not locked, so it agrees. Then it initializes lock to be true, which means the contract is now locked. So now it sends the ether to this receiver address. The receiver address gets the ether and try attacking the smart contract. In doing so, it calls the same send with call method. But since this line has not been run, since the line stopped here, this is where the line stopped, and this line has not been run, so locked is still true. This comes back down here, try checking locked, and locked is still true, so it knows it's an reentrancy attack, and then it throws an error. So that's the way we can catch reentrancy attack. There are many ways to catch reentrancy attack. It depends on how your contract was created. In summary, because the transfer and send function use a fixed gas amount, they should be avoided, except you're the owner of the other contract and you are sure you did not make any state changes in the fallback method. Make use of the core method carries a risk regarding reentrancy. You have to make sure you write a code, a guard, to prevent reentrancy vulnerabilities or attacks, just like we did in this contract. That's all for this video. Hope you learned something new, and we're almost done with this series. Thanks for sticking around so far. Please share this video to people which you feel like will be beneficial to them, and like this video so it can be recommended to others. If you got confused on any part of this video, please leave it in the comment section below, as I will be glad to reply you. By the way, I will soon make a video on how to create your very own ERC token and some other smart contracts which you make in the future. Please subscribe and turn on post notifications so you can be among the first to get notified when we release those videos. Thanks for watching, and I'll see you in the next video.